Okay, this is a short video aimed at my current third year aircraft design students at Swansea University. Over the last week or so, quite a few of you have been coming to me asking for help with the formulation of a MATLAB program to estimate your aircraft's skin friction value. This is something we looked at in the lectures a couple of weeks ago. You've been trying to put this into practice and are having some difficulties, so hopefully this movie will help you with that. First, I just want to say thanks to Dr. Sean Walton here in the department, who helped me get all this set up on my new little tablet here. I am using a new software setup, so bear with me if this doesn't go as smoothly as I would hope. If you're on Twitter, it's worth following Sean. He's at Dr. Sean Walton, and he uses a tool similar to this to do little online tutorials of various engineering concepts. So let's just remind ourselves what we looked at in the lecture. I suggested that at this stage, in the preliminary design stage, you could estimate the frictional drag, the skin friction drag across the fuselage of your aircraft using what you see here. And I suggested that there were two estimates of the skin friction coefficient that you could use. One, a laminar skin friction coefficient, which is the top CF value on this slide, and a turbulent skin friction value, the bottom one on this slide, and that there'd be a transition point when your the boundary layer that's growing along the fuselage of your aircraft in the streamwise direction gets larger, or where the square root of the local Reynolds number goes above 1,000. And that there's a little formula that you would need to set up down at the bottom here to integrate the skin friction along the length of your fuselage. But putting that into practice is turning out to be perhaps a little more complex than you thought, hence the queries. So let's assume that you, by this stage in your design, know the shape of your aircraft's fuselage. So this could be just you've got a set of points that define it. It could be that you've got an analytical function that defines it. But if we say that x is measured in this direction from the nose of the fuselage, in some form or other, you have a definition of the fuselage perimeter as a function of x. So as you travel down the fuselage in this direction, you know how the perimeter, the distance around your fuselage, p, varies. And what I suggested that you should do in terms of the approach to solving or computing that integral, using something like Excel or even better MATLAB, any compute language you could do this in, but I'm recommending MATLAB, would be to break this body up into a set of chunks or slices. So you chop the fuselage up, and we'll look at it slice by slice. Now, if your overall fuselage is of length L, let's call these slices. So each of these is a slice, and if they're all the same length, then of course the length of each slice is simply n divided by the number of slices. So these are some of the numbers that you would set up at the beginning of your little MATLAB program. And then basically it's a case of saying, well, let's loop over each of the slices, and you could, obviously, the more slices you do, the longer your MATLAB code will take to run, but the more accurate your result will be. So you're going to set up a loop that just says, okay, for, let's call it I slice equals 1 to the number of slices. So we're going to create a loop from 1 up to n slice, where you must have declared n slice in advance. Well, we're going to assume that we know what the perimeter is on each chunk, because you know that you're going, that the x value, your local coordinate, goes from 0 to L. So you can work out what your x coordinate is, first of all. You can then, from that, work out what the perimeter is. You then, of course, know what the area is of each slice. That will simply be p times x. And this is the only tricky bit, really, and I think this is what has been confusing people, is remembering that the Reynolds number that's mentioned in the skin friction coefficient is a local Reynolds number. So rather than it being, so we always think of Reynolds number as being rho v some characteristic length over mu. L is usually some global length scale, but we're just going to replace that with the local length scale, which will be the distance x along the fuselage. So our REx value is simply rho v x over mu. So the next thing we'll work out is what is the local Reynolds number. So you work that out. And then you have to ask the question, well, is at this point along the fuselage, is the boundary layer laminar or turbulent? And for this we need a conditional statement, an if statement. So at this point we'll say if the square root of your local Reynolds number is less than 1,000, well, then the skin friction coefficient is your laminar function. Okay, I'm not going to actually write it out here. You've got that on your slide. Well, the local Reynolds number is always going to be greater than 0, so if it's not less than 1,000, it's going to be greater than 1,000. So if it's not less than 1,000, then we're going to just say that the skin friction coefficient is the turbulent value. Okay, and I guess that's the only little complexity here in the code that you're going to write. We just zoom back to the integral that we're trying to compute. The total frictional force is your dynamic pressure multiplied by the local skin friction value times by the perimeter and then integrated. So this is kind of so what we would do in the context of our code here is simply go F, the skin friction, and what we needed to do up at the top of the program is initialize this F value. So before we start our loop, we'll go back up to the top and we'll say right up at the top here, F is equal to 0. And we're just going to simply add up all of the F values on all of the chunks or the slices as we go down the fuselage. So F is equal to the previous value of F. Of course, the first time you come through this loop it'll be 0, and then every time you come around it will add on, is equal to the local CF value times by the area of the slice, so that's the perimeter, times, sorry, I've made a little mistake up here, this of course shouldn't be X, this should be the length of the slice, or the width of the slice. So times A times Q, which is something perhaps you should pre-compute up here at the top of the program, and then that's it. You just end the loop, and that literally is all you have to do. I mean, I said that you could probably write this in 15 to 20 lines of MATLAB code, and I think that probably is the case. So that's the structure of the code you would be going for. So let's just clarify what you've got there. You've got a for loop here, where you're looping over each of these chunks, 1, 2, 3, 4, and so on, until you get down to the final chunk or slice through your fuselage. And embedded in that, you have to ask the question, well, which CF value should I be using? I've computed the local Reynolds number for that slice, and based on that, I'm going to select whether I'm using a laminar skin friction coefficient or a turbulent skin friction coefficient, and then you just add up the forces, which is what you're doing here on each of those slices, to get your total skin friction force. And this will give you a reasonably good estimate at this stage, considering we're very early on in the design process of your aircraft. And in a few weeks' time, when you start running some full viscous CFD simulations, you'll see how good this approximation is to the skin friction value for your aircraft.